Now let's talk about the Henderson-Hasselbalch equation. First of all, we'll write the equation of acid dissociation. In order to have the proton's concentration alone on one side, we'll multiply both sides by the acid concentration and divide both sides by the base concentration. You know that pH is the negative log of H, so we'll apply the negative log on both sides. According to the log rules previously discussed, you should notice that this term is multiplied by that one, so we can simply separate them and insert a plus sign between the log of each one. Sorry, I missed the brackets. Now we'll open the brackets. And you can now replace minus log Ka with pKa. And here we have the final equation. You can simply change the negative sign by inverting the acid to base ratio. Of course, you don't have to memorize all these steps. You should only know the final equation. Now let's talk about titration, which is the addition of measured amount of base to measured amount of an acid, or the opposite. This process will be done while measuring the pH of our solution. And then we'll plot the titration curve, pH against the equivalent amount of base added. 1 is the amount of base required to neutralize the whole amount of acid, and of course 0.5 is to neutralize half the quantity. I guess you notice that there is a middle zone around this midpoint, where pH changes are minimal. This zone extends approximately 1 pH unit above and below the midpoint. At this point, the pH of the solution is equal to the pKa of an acid, or the base being titrated, and I will tell you why in a second. The midpoint is called the inflection point, and the point at which the acid is completely neutralized is called the equivalence point. At the beginning of the process, the acid form is the predominant, and as the titration proceeds, conjugate base of the acid builds up and predominate at the end of the titration. At the inflection point, both forms are equal, and if we looked at the Henderson equation, we will find that their ratio will be equal to 1, and log 1 is 0. That's why pH is equal to pKa. Now here we'll talk about buffers. Buffers are solutions that resist changes in pH upon adding acids or bases. The idea of buffers is based on the zone we previously discussed in the titration curve. We'll apply an example on the pH equation and we'll see why doesn't the pH change a lot near the inflection point. Imagine that we are at the inflection point now and we'll continue the titration. The concentration of the acid and its conjugate base are equal at the beginning, and then the base starts to increase and the acid decreases with equal increments, while adding the same amount of titrant each time. The trick here is the increase in the acid-base ratio each time is getting larger as the difference between the acid and its conjugate base increases. And that's why as we go far from the inflection point, the pH changes faster. We can now have an important conclusion. If at any time you want to prepare a buffer for a solution of a certain pH, you should choose an acid that has a pKa equal to the desired pH or at least near it. And you should adjust the acid and its conjugate base concentration so that they'd be almost equal to each other to have the maximum power of your buffer. One of the important buffers in our bodies is the dihydrogen phosphate monohydrogen phosphate, where the dihydrogen phosphate acts as an acid and the monohydrogen phosphate is the base. By the way, when you prepare a buffer, you should not only focus on the acid-base ratio, but you should take care also of their absolute quantity. Simply because if we had the correct ratio but you have a few amount of the buffer, any small quantity of any added acid or base will use up all your buffer. This gives rise to the term buffering capacity. Buffers prepared in adequate quantities will have high buffer capacity, and vice versa. This is why the dihydrogen phosphate buffer is only effective inside cells, but in blood its concentration is not high enough to act as a buffer. In blood, the buffer is carbonic acid bicarbonate. This is the general equation for the buffer. The dissolved carbon dioxide and water forms the carbonic acid, which dissociates to proton and bicarbonate. Although the pKa of carbonic acid is far from the blood pH, it is still acting as a buffer. This is because carbon dioxide is a gas. If under any circumstances the pH decreased, the equation will shift to the left and the carbonic acid will return to the carbon dioxide, which will be exhaled through hyperventilation and the pH will be restored back to normal. Lungs and kidneys play an important role in this process. Because lungs control the excretion of carbon dioxide, excess excretion can lead to an increase in the blood pH, This condition is called respiratory alkalosis. Respiratory acidosis will be the condition if the carbon dioxide is not well excreted. Kidneys control the absorption of bicarbonate from the filtrate. If excess bicarbonate was excreted, the pH will decrease and the resulting condition is called metabolic acidosis. And of course, metabolic alkalosis will be the condition resulting from bicarbonate accumulation due to inadequate excretion. If any of these disorders occurred, the opposite will take place to compensate for the changes in the blood pH. Thanks for watching, and please feel free to ask a question or post a comment.